Next up, Matt Rainwater, a software developer, with their talk on examining Magic the Gathering rules templating as a regular language and how we can implement it. Also, if you could tell me what a regular language is, because I think I know what it is, and I clearly don't.
Oh, we'll go over that. Don't worry.
Yee.
All right. So hi, my name is Matt Rainwater, and I love board games. I love card games, and I love video games that are basically just board games and card games. And I especially love Magic the Gathering. So welcome to my talk. This is Magic the Regular Languaging, an examination of Magic the Gathering's rules templating as a regular language. This is going to hopefully be a practical guide onto how we can use the concepts of language theory to code a card game. It's going to be an overview of simple regular language represented by what's called a non-regular grammar, which we'll get into later, and how we can use that to store and load our card data in order to make a more maintainable, extendable code base. So let's start by talking about some pretty common card game mechanics. So in Magic the Gathering, in Hearthstone, in any of these games, you play a card and they do something. In this case, we have the Clarion Cathars from Magic the Gathering, and it does a pretty simple effect, which is when it comes into play, it gives you a token. And I wanted to go over this real quick, just so you have some brief context into what we're going to be looking at as I go into some of the code and what a regular language is. But before we do that, I want to go over some common issues that you'll find in digital card games. This is a bug tracker for Magic the Gathering Online, and I've kind of highlighted a couple of the bugs that they're both very similar effects that are used throughout the game. So theoretically, they should be executing the same code. That code should be able to be unit tested and manually tested. But for whatever reason, these two cards have the same ability, but two different bugs, and there's dozens of cards that have the similar abilities that do not have this bug. And this is kind of a sign that they're not designing these cards in a more maintainable way. They're probably doing them individually or ad hoc. Another problem you'll see, this is from Hearthstone. So these two effects, put a random demon from your hand into the battlefield, and summon a random demon from your hand. These two effects are completely identical. I don't know why they're worded differently. I don't know who decided that. I don't know if it was a design choice or just it kind of happened. But to me, I see this and I go, oh, okay, they're not using their actual like game logic to structure their UI, which could be a design choice, that could be meaningful, but it does make it to where if something does change, the rules might not be updated correctly in the actual card. Let's see, and then the third thing I want to bring up is this is decompiled Slay the Spire. As you can see here, every single card in that game has its own class, which to me is baffling. If you go into the code, they do have kind of separate components that make the whole card, but you get weird things like here at the bottom you see strike_blue. That's the basic strike card that is in every character. There's a strike blue, there's a strike green, there's a strike red. No reason for those to have different classes. I don't know why that happened. And to me, this shows that he's able to compartmentalize parts of how a card operates, but for whatever reason, he decided to kind of put that all together, or whoever designed it, developed it, decided to put it all together as individual classes. There can be some benefits to this, but I see it, and I just see a waste of code and more code that you have to maintain. So these three problems, I'm hoping that I can show how I can solve those, and we're going to do that with regular languages. So this is going to be a pretty simple explanation. Wikipedia has very good articles on regular languages and regular grammars if you want to really learn what they are. But what I'll say is you can think of a regular grammar as a set of patterns that a string has to follow in order for it to be part of a regular language that grammar represents. So if you see here on the left, we have a regular grammar which says, okay, you start at S1, and then that gives you a 1, and then another S1, or it can give you a 0 and an S2. An S2 can give you a 0 and an S1, an S2 can give you a 1 and an S3, And an S3 can give you an epsilon, which just means the end. Regular grammars can also be represented with finite state automatons. Have you ever seen one of these before? They're pretty simple to follow. You start at S1, and then you can follow either of the two arrows that lead away from it based on what input you've been given. Oops. So if you get a 1, you just kind of circle back and go right back to S1. If you get a 0, you hop over to S2. And from there, if you get a 1, you go to S3, and the double circle there is kind of the same thing as the epsilon. That means the string's over. So to give a couple examples, the string 0, 1 fits because you start at S1, you go to S2, and then, you start at S1, you go to S2, you go to S3, and you're done. A slightly longer one is also fine, as long as it has an odd number of zeros, because you have to go S1, S2, S1, S2, S1, S2, S3. We can get a little more complicated and have this go over and over to S1 before we start making zero loops and eventually ending on S3. But something we can't do is end on, we have to end on 1, and we have to have an odd number of zeros. So 100 would go from S1 to S1, S1 to S2, S2 to S1 and stop. But S1's not a terminal state, so that one wouldn't fit. And yeah, I did see in chat someone asked if 1 and 0 conditions. These are characters in a string. So as we're interpreting the string one by one, we have to determine whether or not it fits our regular grammar rules. This could have been A and B. Usually you'll see it as A and B, but I did 1 and 0. And I want to kind of stress that regular grammars and finite state machines will represent a regular language, but technically you can represent a regular language with what's called a non-regular grammar. If you want to know exactly what that means, you can ask me or look on Wikipedia, but it's not super relevant. I just wanted to bring it up that in case anybody's better at this than me, which I'm sure that someone is, you can you can ask me about it later. But so let's look at a magic card again. Let's go back to something simple. So here we have that same card from earlier, Clarion Cathars. When it enters the battlefield, create a 1/1 white human creature token. But first, we're going to break this up into different parts. So when Clarion Cathars enters the battlefield, we're going to call that a trigger, and create a 1/1 white human creature token, we're going to call an effect. We'll call the whole thing an ability. So an ability is comprised of a trigger and an effect. Now, this is going to help us generate a really simple grammar that we can then use to encode the card's ability. So here we have that grammar I just talked about. If you see here, an ability is comprised of a trigger and an effect. A trigger is comprised of a cause and a source. Anything in italics is going to be kind of a variable where you'd look on the left side to find how it gets formed, and anything in all caps is just a straight string. So source can only be the word self right now. We're not going to let it be anything else. Cause can only be enter the battlefield, ETB. Create token's a little more complicated. It's the string create token, and then it's a bunch of variables. A number, a power, a toughness, a color, and a permanent type. But at the end of the day, what this grammar allows us to do is give us an expression that represents this card. And it's just one line, ETB, self, create token, 1/1/1, white, creature, human. And so now, in our actual data, whatever file you're loading all your cards from, that's the only line of data you need to represent this card. But we want to do more than just, make this specific card and nothing else. So I'm going to show you a slightly more complicated grammar. It's got the same basic variables, but now we can do things like we can trigger off of other creatures entering the battlefield. Other creatures doing something, including entering the battlefield, dying, or attacking. Our effects can now be to create tokens or to gain life. We can have any number within those 3 variables. We can have all the colors of magic. We can have all sorts of subtypes and permanent types. We can do all sorts of stuff with this as long as we code it, which is what I'm going to show you guys now. So here we have a pretty simple parser. All it's doing is it's taking these cards. I write 4 of them right here, taking them line by line and breaking them up into words, which are separated by spaces. So self is a word, ETB is a word, create token is a word. And that's what our parser is doing. and then it's passing them into these classes in order to actually instantiate our cards. So as you see here, it's going to make a card with an ability, parsing in the words. And I want to specify that, I want to clarify that the words are a queue. It's not a list or an array or a set. It's specifically a queue. We're going first in, first out. So as we go to ability, we can see that when we parse an ability, all it does is it just passes that queue into the trigger, and it passes that queue into the effect. If we go into the trigger, all it does is pass that queue into the source and pass that queue into the cause. If we go to source, all it does is dequeue. Finally, we're dequeuing, because this is where we're actually getting to these terminal ends, where we're pulling out something. And then once it pulls that out, it kind of goes back up to the trigger, right? And then tries to get the cause. Well, the cause just grabs the next thing in the queue. And this is an important feature of regular languages, is that in order to be represented by a finite state automaton, FSAs don't have memory, and they don't have the ability to kind of look back and see what else happened. They don't have the ability to store things for later. All they can do is look at what they're looking at right in front of them, which is why this is represented by a queue. It's just going to be looking at whatever's at the front of the queue, dealing with it, getting rid of it, forgetting about it. But yeah, so as we parse out this trigger, then we go into the effect, which is pretty similar. It does a little bit of reflection in order to make a class for create token or gain life, but it does the same thing, where all it does is look token by token or word by word, parses them, and instantiates this class. So if we go back to these cards real quick, I just want to kind of go over what they are. This first one is the same thing as the Clarion Cathar. It creates a 1/1 white creature. I made one that makes 2 1/1 red creatures, goblins. One that just gains you a life, and then a slightly more complicated one that when another creature enters the battlefield, gain 1 life. So let's go ahead and run this, and I wrote a quick and dirty UI over it and some very simple rules to actually perform these operations. That's not really part of what I did, but all the source code for this is on GitHub, and I'll share it after the talk. Let's see. Come on, there we go. Whoops. All right, so as you can see, it says, we have 20 life, nothing's on the battlefield, nothing's in play, and I have these cards in my hand. So if I were to play, when a creature enters the battlefield, it gains 1 life. Right away, it doesn't do anything, because I haven't entered any creatures. But if I were to cast, say, the second one, which creates 2 1/1 red goblins, what do you know? My life total is 22. So that's a pretty simple approach. But what I really want to show here is, let's go back here. Someone in chat, post your favorite creature and how tough it is. Okay, Summer's typing. Darksteel Colossus. Darksteel Colossus. And he's an 11/11. That's a big boy. So if I run that, all I did was type 1 new line that I mostly copy pasted from an existing line. Oh, he's red. He's not really supposed to be red in the real world, but that's fine. I meant more like just name a random magical creature, but specific Magic Gathering cards is fine. So there we go. So now we already have this card. When this effect enters the battlefield, create an 11/11 red Darksteel Colossus creature token. And an important thing I want to bring up here is, I'm going to go over these kind of 3 things, and then we can go to questions. The cards they're comprised of generic parameterized classes that represent the different aspects of the card. That means in order to make a new card, I didn't have to write any new classes. I didn't have to write any new code. I just wrote a line, and suddenly I can have a 11/11 Darksteel Colossus. In addition, we can kind of reverse translate this into human readable text. So I didn't write out, when this effect enters the battlefield, create an 11/11 red Darksteel Colossus. I just interpret that from the language we have here. And then the third thing, and probably the most interesting thing, is this is really easy to mod. If I gave this to somebody, they can make whatever card they want. They wouldn't even have to really know a programming language or anything. They could just look at existing cards or look at whatever documentation I have and be able to just make their own cards. All right, so that is the code, and like I said, it's on GitHub. I'll show it to you guys later. And if there's any, do I have time for questions? Let me see. If I do, feel free to ask them. I don't. Never mind.
But thank you so much.
All right. No problem. I'll be in the chat room later.